Okay, so with that, let's go to the hackathon. Hackathon notebook is going to be this 4 p.m. Hackathon digital twin. Okay, and there's a description at the top. It's a guided workshop built around simulating diffraction patterns. The opening sections, there are a couple worked examples to give you some tools you can use to solve the problem. So you're going to be acquiring additive diffraction data, segmenting particles, and trying to figure out patterns in the lattice parameter across the different types of particles. So what's going on under the hood here is we're using asynchronoscopy and just starting up a digital twin server. The nice thing about it is you could, instead of starting this up as a digital twin, you could just put in the IP address of the actual microscope down the hallway, run the exact same notebook, the exact same code, change nothing, and you could just click run all and it would work. So maybe if anyone has a really good solution, then you can email it and we'll try to run it on the microscope later. Okay. So we'll run the first cell. We're installing UV, this package manager here, cloning if we don't already have it, which I don't think we should by this point in the day. Asynchronoscopy from GitHub. You have to install some extra dependencies in asynchronoscopy for the diffraction digital twin. So some ABTEM and atomic simulation environment packages, but it's all automatic. And then interactive plotting, of course. So I'm going to run you through the first few cells, and then there's a problem statement at the end, and everyone will be turned loose for an hour. Taking a while. Awesome. Again, we'll go runtime, restart session, and then run the next cell. This is going to run the servers in asynchronoscopy with a setup that's based on this diffraction digital twin. And so these are all going to run locally inside Colab. That's what this 127.0.0.1 means. always take much longer in the evenings. Okay. All the servers are ready. Okay, we'll load in our packages. These are some of the asynchronous specific imports that we need. Connect to all the device servers. Okay, here we go. We have a scan device. We have our instrument. That's our microscope control, and then data server. Okay, this client here is going to be serving us all our data. So when we call acquire, it saves the image, and then this client is what we'll use to get the data. Right now we have 0 data, but we'll fix that. So when we call microscope.acquire scanned image, it's going to return us this data key. That's just an HF5 file with a timestamp saying it's a stem image, and that's the time it was taken. When we call client key image to get the image, and there's some metadata stored in there as well, like pixel size, stuff like that you might need. Okay, here's our overview image. We have some nanoparticles. There's really no scale bar, so maybe we check the metadata and see what sort of scale. Oh, it's empty. Well, that's not too good. Oh, I see the issue. Okay, to get the actual metadata, you don't just get it off the image, you get it off the HADF channel. So okay, so there we go, field of view, and we have 500 nanometer field of view. Okay, it's good to know. So then these particles are something on the scale of tens of nanometers. And so just looking at the image, you'll notice one thing immediately. Well, a few things. There's different sizes. Some of them are more circular, and some are more ovular. And this is all just simulated, but I tried to build in many different patterns to see how much you can discover in an hour. And so I'll go ahead and give you a hint. The circular ones and the ovular ones have some differences in lattice parameter, a couple differences. And it's going to be your job to find it out. So I have some code cells here that are meant to help you. First, let me show you how to get a diffraction pattern. You can place the probe like this. So if you just hover your mouse, you'll see the pixel position in the bottom. Right now, my mouse is at 439, 298. And so you can put those numbers in here, 439, 298, and then microscope.place beam to move the probe to that position, and then you'd call acquire camera image to get the diffraction pattern. And this should look familiar after today. Here's our nano beam diffraction pattern. This is going to be different for every particle that you put it on. They have different rotations, different lattice parameters. And again, it's going to be your job to figure those out. So a couple other tools that I have to give you. First, we'll take another image here, overview image. Okay, it's the same image. Here's the first tool, is some code to threshold and get each of the particles. So here they each have a label and we'll compute some statistics for each of the particles. In a real hackathon, we would do this all on our own, but since we only have an hour, this is what we have. So here we'll plot some of those statistics from the different particles. Okay, on the left, we have area versus radius. That's not very informative, but more informative as it goes on. So they have this circularity marker, covariance aspect ratio, and radial bound, which is like a min-max ratio. So hopefully some of those trends help you identify different types of particles to investigate. And the last tool that I'll give you is some code to get from the diffraction pattern to a scalarizer, the lattice parameter. Mm-hmm. Okay, so it identifies the zero beam, deconvolves the diffraction pattern with the zero beam, and then I didn't want to make it too hard, so everything was already pre-centered. I didn't put any image shifts in the diffraction pattern. And so you can just take the radial profile and use that to get the first Bragg peak and back out the lattice parameter. So that's all in a function here called getLatticeParameter. You input the diffraction pattern and the pixel size. So that's going to be a really useful tool. And there are 3 exercises for the hackathon. We're 10 minutes in, so we have about 50 minutes left. The first exercise is going to be compare center to edge lattice profiles. So essentially just measuring in a line across one of the particles and trying to see how the lattice parameter changes. Exercise 2 is trying to use some of the reconstruction algorithms that we learned in the previous notebook. You can just copy and paste some of those cells to measure the particles sparsely and then reconstruct a map of the lattice parameter from those measurements. Exercise 3, define a smarter grid of starting points to measure and then trying the reconstruction. So in other words, you can just randomly sample on the particle, grid sample. You can sample at one place, have some reconstruction loss that informs your next measurement, or use some type of neural network prior, like you suggested. And then exercise 4, this one is really hard level. Map the whole field of view, map all the nanoparticles, lattice parameters. And then it'd be interesting to see if anyone can do that, who can do it in the least number of measurements and use some reconstruction. So, happy hacking. Okay, so as the day's coming to an end, we have just a few minutes left, but I'll go ahead and check in. Was anyone able to figure out the difference in the ovular nanoparticles and the circular ones? Difference in lattice parameter? Okay. They're off by about 25% from each other. I think the ovals were bigger. Then another pattern, did anybody guess? I think ovals starting in the middle, they were the biggest, and then they shrank going outwards. and then the circle is expanded going outwards. So the last perimeter grows. Then yeah. No, it's all simulated. Yep. If you want to see the digital twin, you can go to yeah, if you want to see how it's done, it's asynchronoscopy. Go in the instruments tab, and it's called diffraction digital twin or something.
So you made a GUI, right?
Yeah.
So then you download it, you can make user interface, and then you can select, you can have a list of all the different things that are available. So you can easily make new ones.
Did anyone see a pattern on the edge of the particles? About 5 pixels from the edge, the particles become amorphous. So the radial sum would just go right downhill and probably cause some problems. So that was the other, I think those were all of the patterns. Did anybody get adaptive, like a map where you just take a few measurements and then you get the map going with the reconstruction? No? Okay. Keep working on it then. Yeah. It was a lot to do in an hour, so.
Yeah.
Okay.
That the idea, so the idea from the last one, the last one.
Oh yeah, so the idea was just copy the code over from the 3 p.m. notebook and use it in this notebook because you have an image or sampling a scalar. So keep playing around with it, and then if you get anything good, then just send me your code and we can run it in real time on the microscope. We don't even have to change anything. So that's it for the hackathon.